Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem number of longest increasing subsequences. And before we even get into this problem, I just want to mention that this problem is actually very similar to another problem that we've already solved, which is longest increasing subsequence. As the name suggests, both of the problems are very similar. So this problem really just extends the idea of finding the longest increasing subsequence. Basically, we want to find not only the length of the longest increasing subsequence, let's say the length of it happens to be 4. In that case, we want to find how many subsequences, how many different subsequences are there that have this length, which is the max length, right? So we're counting the number of longest increasing subsequences. And basically, we're given an integer array of nums. We want to return and count the number of longest increasing subsequences. And LIS, which is what we're going to be calling it for short, has to be in increasing order. A subsequence basically is like taking an array like this and taking some of the elements. You could take all of the elements or you can take a subset of the elements. So for example, we don't take the 5, or let's say we don't take the 4 either. So we're left with a 1, 3, 7. And we have to keep these values in the same order, the same relative order that they appear in the array. So basically this is one subsequence, 1, 3, 7. A subsequence though is not enough. We want to find the longest one. We want to find the LIS. So in this case, there's actually two LISs. One is 1, 3, 5, and 7. So we remove the 4 because if we leave the 4, then it's not in increasing order, right? We can't have a 5 and then have a 4 that comes after it. The 4 is smaller, right? So we can't keep the 4 in. This is one LIS, but we could also have chosen to remove the 5, right? If we remove the 5, it's still in increasing order like this. So we know the LIS, the length of it is 4. How many were there? The count of them, there were 2 of them, so we returned 2. So I'm going to show you how to solve this problem, and we're going to be doing it using dynamic programming, and we're going to solve it with n squared time and big O of n extra memory. But before we even get into the DP solution, let's just start with a little bit of intuition. If we wanted to generate every single subsequence using this input array, we would basically, for each input value like 1 or 3 or 5, we really have two choices. We can either choose to include this value in the subsequence or not include this value in the subsequence. If we were doing a decision tree, for 1, we can either include 1 or we can skip 1. And we could do this with every single value, which would allow us to generate every single subsequence, right? For the second choice, here we have include the 3 or don't include the 3. Here we also have that same choice, include the 3 or don't include the 3. So just from the first two values, you can see all the subsequences that we can create. We can create technically 4 of them, right? 1, 3, or just 1, right? Where we skip the second element, or skip 1 and then we're left with just a 3, right? Or this one, which is basically no elements, right? I guess technically an empty list is a subsequence, but it's not really relevant for this problem. And if we just continue generating the tree, we could create every single subsequence. Now, I'm not going to follow this logic in this problem because we don't want every subsequence. We want only increasing subsequences. So I'm going to follow the dynamic programming logic, which will allow us to generate the longest increasing subsequence. So if you wanted to find the LIS recursively, you could make a bunch of choices. The first choice would be what's going to be the first value in our subsequence. Well, we could pick any of the values. We could pick the 1, we could pick 3, we could pick 5, 4, or 7. Now, for each of these branches, we can only choose new elements that come after the original value. So for 1, we're allowed to choose any of the 4 elements that come after it. For 3, we're allowed to choose any of the other 3 elements that come after it. And for 7, there's not really any elements that come after it, so we can't choose anything. So in this case, this is the terminal case. If we start with 7, the longest increasing subsequence we can create is just 7 itself. There's no other elements that come after it. So this is the LIS starting at 7. What about for 4? Well, 4 is also pretty simple because there's only one value that comes after it, 7. But is 7 actually greater than 4? Because if we're creating an LIS, the values have to be in increasing order. For 4, 7 is greater than it, so that's fine. What about for 5? Well, the next element that comes after 5 could either be 4 or it could be 7. We know that 4 doesn't even work for us because it's smaller than 5, so we're not even going to consider this path, right? So the LIS starting at 5 happens to be 5, 7 of length 2. And now let's move on to 3. We actually have 3 values that come after 3. We could pick 5, or we could pick 4, or we could pick 7, all 3 of these choices are valid because all 3 of these numbers are greater than 3. But so now we have some subproblems, right? For 5, we actually have a couple elements that come after it, 4 and 7. And for 4, we have exactly one element that comes after it, 7. And for 7, we know that there's no elements that come after it. But you might just be noticing that this subproblem over here and this subproblem as well, we were originally asking what's the LIS starting at 3, but now we're asking what's the LIS starting at 5. But remember, we actually already solved that problem over here, right? Good thing I started all the way at the right side and then we started working our way left, because if I had started from here, we wouldn't have known that we already solved this subproblem. And by now, if you're familiar with DP, you might be recognizing why this is a DP problem. Because we could solve the problem recursively like this and also implement caching, which would lead us to a big O of n squared solution, or we could just skip straight to the DP solution, because now we've realized what order we should be solving these problems in. We should be solving the subproblems in reverse order. We should be finding the longest, the LIS starting at 7, then at 4, then at 5, then at 3, then at 1. And if we do it that way, we won't have to repeatedly solve the same exact subproblems. So in this case, for 5, we already know there's an LIS of length 2 that starts at 5, and there's exactly one LIS of length 2 that starts at 5. Because in this case, for the context of this problem, we're not just looking for LISs, we want to know how many are there, because that's what we want to return, the count of those LISs. So just adding a little bit of illustration to make this a little bit simpler to understand. But so assuming that we don't actually resolve these subproblems because we already solved them before, now we have discovered that for 3, the LIS is of length 3, and we know that there's actually 2 of them, right? So we're keeping track of 2 pairs of values. We want to know what's the length of the LIS, and we want to know what's the count of those LISs, like how many subsequences of length 3 are there? Well, there are 2 of them. Now let's actually kind of understand how we can solve the dynamic programming solution without even using a decision tree like this. The logic is very similar. So as we were solving the recursive problem, we noticed that solving subproblems, smaller subproblems, and then solving bigger ones is a good order to do this in. So we're going to start all the way at the right. And so this is our nums array. These are the values. These are the indices for each of the nums. For each of these, let's say we're starting from here. And the value that's going to go in our DP array or cache or whatever you want to use for this, clearly we have a pair of values, right? So the value that's going to go in this spot is going to represent the length of the LIS starting from index 4. And the value that goes here is going to represent how many were there, right? The count of those LISs. Similarly, the values that go here are going to represent the LISs starting from index 2 in our array. So let's do that now. So starting from here, we know that there's no values that come after it. So what's the length of the LIS? Is it 0? No, because for any LIS, like from any index that we start at, we have at least one value, right? We have the 7 here. Maybe there's no values that come after it, but the 7 itself is still a subsequence, so we can say the length of it is 1. How many subsequences were there of length 1? Exactly 1. So that's really our base case, a very simple case. So what about over here? Well, in this case, there is a value that comes after it. There's exactly one value. Now, the only thing we really have to check here is the value greater than it? 7, yes, is greater than 4. So therefore, if we do include these 2 values together as a subsequence, this is in increasing order. Therefore, we can say the length of this is 1 plus the LIS starting at index 4, which we know is length 1. So what we're going to put here is actually 2, and the value we're going to put here is going to be 1, and the reason is because we're taking the value that came after it and adding it to this one, because these values together are the ones that create the LIS. This might not make sense right now for just 2 values, but as we go through the rest of the array, I bet this will start to make sense to you. So for 5, we actually have 2 values that come after it. One value is 4. Is 4 greater than 5? No, it's not. So we actually cannot include this in our subsequence. So we don't look at 4 anymore, but we have a second value that comes after 5. We have have a 7, and 7 is greater than 5. So what we're going to put here for the length of the LIS is going to be 1 from 5 plus the LIS that starts at index 4, which we already calculated as 1. And how many were there? There were exactly 1. So what we're going to put here is going to be 1 plus 1, which is 2, and 1 here, because there's one LIS of length 2 that we can create if we create this subsequence. Now at 3, we're going to look at the next value. It's 5, and 5 is greater than 3. That's good. So what's the length of this LIS? Well, 5 is not just a value by itself, because we know starting from 5, we can create an LIS of length 2. So therefore, starting at this value 3, we can create an LIS of 3. But just because we found one LIS that we can create doesn't necessarily mean it's the maximum. I've been assuming it's always going to be the maximum, but it's not necessarily the case, because we could, instead of looking at 5, we could also look at 7 and see that, oh, 7 is greater than 3, so the LIS that we can create with 3 and 7 is going to be of length 2, but 2 is not the LIS, right? We found one that's of length 3. So we're not going to put 2 here. We're going to put 3 here, because we found at least one LIS that is of length 3, and that's going to be 5. And we know that the LIS starting from 5 was 5, 4. So this is that LIS. We're just not going through the entire thing, because that's what this DP is for. That's what this little array over here is for, to store that repeated work that we don't have to continue doing. There was one more value that comes after 3, and that's 4. And 4 is also greater than 3. And what's the length of the LIS starting from 4? It's 2. So 2 plus 1 is also 3. So that means we just found our second LIS of length 3, right? One was from 3 to 5. The second is from 3 to 4. So for count this time, we're not going to put 1. We're actually going to put 2, because we found 2 of them. And finally, getting to the beginning of the array, 1, I'm just going to speed through this. So from 1, we look at the next value, 3. 3 is greater than 1. The length of this LIS starting from 3 is of length 3. So we found one possible LIS that we can create starting from 1, which is of length 4. Are there any others that come after it that are even longer than 4? Or also, are there any that come after that that can maybe create an LIS that's even longer than 4? And if there are, then we're obviously not going to put 4 here. We're going to put that longer one, maybe a 5, and then update the count accordingly. Or maybe there are other LISs over here that will also lead to us having an LIS of exactly length 4. In that case, we'll take the counts of those and add them to the count over here. Or maybe there's going to be LISs that are actually shorter than 4. And in that case, which obviously is the case here, we're not going to end up updating our count at all with those LISs, because right now we found one, we found exactly one LIS of length 4, so that's what we're going to put here when we were looking at 1 and then going to 3, but we can also go to 5 where the LIS is 2. 2 plus 1 is going to be 3. That's not greater than 4. Another 2 over here, and then a 1 over here. So none of those are going to make a longer LIS. So this is our finished computation. Oh, and whoops, I actually just realized I made a mistake. We're not actually putting a 1 here. We should be putting a 2 here. And the reason is because when we were looking here and then looking at the next value, we found that 3 plus 1 makes the LIS be of length 4. And what we're going to do is actually take the count from here and then add that over here. We're not just adding 1, we're adding the count from that LIS. So sorry if that was confusing, but now knowing this, how are we going to return the result? Well, in this case, the result is at index 0. The longest LIS is of length 4. How many are there? There's 2 of them, and that's what we were expected to return up above, right? You can see 2, and these are the 2 LISs. But that's not always going to be the case. It's not always going to be at index 0. Just imagine if the value over here, instead of being a 1, was actually, let's say, a 10, right? A 10 over here, then what would be the LIS starting from here? It would not be of length 4, because all of these values that come after are actually smaller than 10. So the LIS here would actually end up being 1. So that's basically just to show you what a counterexample would look like. So the generic way to return the result here is going to be scan through this basically, or as we are building this, just maintain what the max LIS length actually is. In this case, it's 4. And then for that, add up all the counts corresponding to that LIS. In this case, there's only 1, but it could have been different. suppose this value actually didn't even exist, and actually suppose this value didn't exist either. In this case, we have the max LIS being of length 2, and there were actually 2 of them, right? There was one over here and one over here. So what we would do is return the counts added up, which would end up being 2. So after all of that, we're actually finally ready to get into the code. So let's do that. So now let's code up the DP solution. But by the way, if you do want to check out the recursive solution as well, I have both the DP and recursive solution on my GitHub, and you can check that out with the link in the description below. All you have to do is pay me $1,000. Just kidding, it's perfectly free. So check it out if you want. But now let's actually get into the code. So I'm just going to copy and paste a couple quick lines first. The first thing is our DP cache, or our array that we were trying to compute. Now in this case, I'm just using a hash map because I'm lazy, and hash maps can be used as arrays if you want, but you could just use an array if you'd rather do that. But basically in this case, the key of our hash map is going to be the index, right? And what the index really corresponds to is the starting value, right? Are we starting at index 0, index 1, index 2, etc.? And the value of the hash map is going to be a pair of values, similar as I showed in the drawing, where one value of the pair is the length of the LIS, and the second value is the count of that LIS. And we also have 2 little variables over here that are going to be, as we compute these variables are going to be maintaining what is the max length of the LIS that we have seen so far. And the result, which I probably should have just named count, is going to be our return value. That's why I named it result, is going to be the count of that max LIS that we're also maintaining. So before we even write anything, I'm just going to put our return statement out here because that's what we know we are going to be returning. And then similar to the drawing, I'm going to iterate through the array in reverse order, where I is going to be the start value. Actually, I is going to be the index of the start of our subsequence. And I'm going to iterate through it in reverse order as I showed in the drawing, but you could do it from the beginning if you really wanted to. In that case, if you were doing it from 0 to the end of the array, in that case, I would not be the start of the subsequence. It would actually be the end of the subsequence. But I think this way is a little bit more intuitive, but you can, do whatever you prefer. Maybe as a challenge, you can try doing it the opposite way from what I'm doing. So we're going through the array in reverse order. And what we're trying to do, so starting from index I, what we're trying to do is compute just 2 values. We want to know what's the max length of the LIS starting from index I, and what's the count of that LIS. So from index I, we could look at every index that comes after it. So we can create another pointer j that will iterate over I plus 1 until the end of the nums array. And we could find all subsequences that come after index I. But we want to make sure that those subsequences have a starting value that is greater than the starting value at index I. And we can do that very easily with just an if statement. So we just want to make sure that nums of j is greater than nums of I before we continue. And next, what we want to do is get the length and the count of the LIS starting from index j, and we can get that from our DP hash map that we are computing. So with just this line of code, remember DP of j is going to be a pair of values. The length is the first value, which we wrote up above as well, and the count is going to be the second. So we know that this is already going to be in increasing order, but now the only question is, does this subsequence allow us to create a max LIS? And to check that, we'll have to compare it with these 2 values. So what I'm going to do here is check if length plus 1 is greater than our current max length. But why am I doing length plus 1? Well, we know this length came from DP of j, but we're adding one more value to that subsequence, which is the value at index I, so that's why we're saying length plus 1. Is that greater than our current max length? And by the way, our current max length was initially just set to 1 because we were just considering the subsequence that is the value at index I itself, right? Just a subsequence of 1 value. So if it is greater, then we are going to be updating our current max subsequence length and the count of it to just be length plus 1 now, as well as whatever the count was from that subsequence, that LIS at j. And the else case is simple. If we obviously don't find one that's greater, we're not going to do anything. But there's one else if case, if length plus 1 is actually exactly equal to our current max length. that means we found another subsequence that's of the same length. So we're not going to obviously update our max length, but we are going to update our count. We're just going to take the count, our current max count, and add to it the count of the LISs starting from J. So just taking the count that was extracted from that pair of values to here. Okay, so that's the main logic that we were going for in our DP. There's one little thing we do have to change though. Here, I declared two variables just to make this a little bit more readable. But what we really want to do is store these variables in our DP. So what we're going to do after this loop executes and we have finalized these two values, we're going to say DP at index I is going to be set to this pair of values. Max length goes first and next goes max count. And this might look like the entire code, but also remember we wanted to return the result and we were trying to maintain the result in these two variables. So let's actually add some code to do that, to maintain as we go through this. What's the max LIS we have seen so far in total, right, throughout every single starting index, and how many were there? And to do that, we're basically going to follow a very similar logic that we defined in this if-else statement. So what I'm going to do is just copy and paste it, actually. So here we want to know if our max length of the subsequence we just computed right now is greater than the global one that we have been maintaining, which is len lis up above. Then we're going to follow a similar pattern as this. We're going to update these two variables, assign our len lis and our result, which is our count, to this pair of values. So that's if we found a new max. But if we found the exact same max, which is max len is exactly equal to len lis, in that case, we're not actually going to reset both of these values. We're just going to increment the count, and our count in this case was actually set to result, and to result, we're going to add to that max count. So believe it or not, that actually is the entire code. Let us run it to make sure that it actually works though. And as you can see on the left, yes, it does, and it's very efficient. So I really hope that this was helpful. If it was, please like and subscribe. Consider checking out my Patreon where you can further support the channel, and hopefully I'll see you pretty soon. Thanks for watching.